We're dealing with uncertainty and error in measurements. So what is experimental error? We know we're going to be in the lab a lot. There's going to be a lot of errors, hopefully none that are dangerous, but a lot of errors nonetheless. Error is inherent in all experimental measurements. What it is the scientist's job to utilize laboratory techniques that are seen as reliable when repeated by either themselves or by other scientists in effort to reduce experimental error. Significant figures. You got a worksheet on this with all of the rules, but a few points about them more specifically. It's the minimum amount of digits needed to write a given value in scientific notation without losing the accuracy of that number. It is specific to the laboratory instrument that we are using. Our graduated cylinders, for instance, the 10 milliliter, has a different amount of significant figures than our 20 or 50 milliliter graduated cylinder. If we are using an analog device, we measure significant figures by looking at all of the known numbers plus one estimate. Let's take a look at what I mean here. If we have a graduated cylinder, so analog means not digital, not electronic. Oof. Try that again. So, graduated cylinder, and we have 1, 2, 3, 4 milliliters. And let's say my water, due to capillary action, is somewhere in here. We know that this is called the meniscus. And when we're measuring, we want to be on eye level with that. My little eyeball looking at it. I want to be on eye level with it, so I'm going to need to kneel down to look at it. I don't want to hold it up, because if I am, I'm probably tilting it some, which is going to give me an odd value. I'm going to measure from the bottom. So if I'm looking at measuring from the bottom of my meniscus, I know my certain number is somewhere between 1 and 2. So I can say, I know 1 for certain. My estimate, my guess, is that it's at 1 point, to me it looks like a 4. My lab partner might say a 3. Another person might say it looks like it's halfway through, so 1.5. I always want to write down what my unit is. I'm assuming that my graduated cylinder here is at a volume of milliliters. So this again is my one known and one unknown. We always end with whatever our unknown estimate is. Now if my meniscus, let's draw a new one, make this one green. Let's say, go down like that, and I look at my meniscus, and to me, it looks like it's on the 3. Well, I can't just write 3 and be done with it, because I know with this measuring instrument, I'm able to have one estimate, another digit, with this graduated cylinder. So I would have to write 3.0 milliliters. Now that 0 is something that people often forget. Don't forget it. If our instrument can measure out to an extra significant digit past the decimal place, we have to write it down, even if it is 0. If we use a digital device, we just read whatever the device says. So if we're using an electronic balance, and it says it's 12.24 grams, we just write out 12.24. We don't want to make an estimate because there's nothing to estimate. When we make calculations, we want to wait to round and write the correct number of digits until the final answer. So if we're going through a bunch of addition or subtraction, if we're looking for some calculated values, we want to wait until the very end and follow our Sig Fig rules. And this is to avoid accumulated round-off errors. When we graph, we want to make sure that the rulings on the graph paper could be compatible with the number of Sig Figs that we have. For instance, if we have the data points 1.032, 1.547, 1.793, and let's assume that this is analog. We assume that this is an analog value, then each of these ending numbers is my estimate. So my partner might have gotten 1.794 instead. Okay, so the rulings that I draw out should be to the hundredths spot, and the thousandth spot is where I estimated. So it's going to be not on the line of 0.03, it's going to be slightly above. So just like I saw with my graduated cylinder, my data points are going to be doing the same thing. So precision, it's a measure of the reproducibility of a result. And it's found by repeating the measurement several times. If it's precise, then the data points should be near one another. Precision is often used interchangeably with accuracy, however the words do mean different things in scientific terms. Accuracy is a measure of how close you are to the truth. It's a textbook or accepted value. And it's determined by measuring the quantity with varying laboratory techniques. Once we have a lot of varying laboratory techniques, if we have the same value all the time, then we get that accepted value, something that we could see in a textbook. This is an image that you will often see in chemistry textbooks. If we have a target and we have all of our holes that are in one area but not in the bullseye, then it's a low accuracy. It's not accurate because it's not in the bullseye, but since they're all clumped together, it's a high precision. And this, as we're going to see soon, would be caused likely by systematic error. If we have all of the bullets in the bullseye, we've got something that's highly accurate and highly precise, which is what we hope for in the lab. If we have data points that are all over the place, that's low accuracy and low precision, which is bad. We just went through this example in class to get prepared for possible questions that you might see on the exam. If we have those three, then we've got something that is accurate and precise. If we're looking at that clump there, we probably have some systematic error because we're precise but we're not accurate. If we're looking at this one relative to where it is, not relative to the other ones, this is just neither accurate nor precise. So systematic error, we just mentioned it a little bit with the last image. It's also known as determinate error, and it's a consistent error. So we've got something that's precise but not accurate. So we are on the bullseye, all grouped together, but not in the main target area that we're shooting for. And it's detectable, so we know that we're making this error. And it might be after we're done with the lab that we know it, but at some point we're going to realize, oh, I'm consistently making this error. And we can make steps to correct it. And steps should be taken to correct a systematic error. So if you are consistently looking at your graduated cylinder the wrong way, you need to fix that way of doing things, rather than saying, oh, I know I'm systematic error because of looking at my graduated cylinder from above rather than straight on. Okay, you need to fix that behavior and not just say, this is my systematic error. Ways that we can detect systematic error is if the results don't match that accepted value. We just talked about that textbook or accepted value. If the results don't match up and they're consistently either above or below in the same area, we would call that systematic error. We could test a control substance against our substance that we're looking at. We could use a different test method to check for systematic error, and we could have another scientist test it in their lab. Random errors are also known as indeterminate errors. It arises from natural limitations in our ability to make physical measurements. It occurs if there's an equal probability of the measurement being high or low from one reading to the next. So I can't say, oh, this is systematic, they're all clumped together. It's going to be all over the board or all over the bullseye. And it can be reduced by doing repeated measurements. The more measurements, the better. Sometimes we don't have a lot of class time, but you're going to still want to do accurate and precise work. And you want to do it as many times as possible so you can take some averages. When we are in the lab and we're writing out our error values, if we're using an analog instrument like a triple beam balance or graduated cylinder, you're going to write all of the known numbers plus one estimate. We just saw that a little bit ago, plus or minus the error to that decimal spot. So if we have this one, 36.712 as my value of my analog device, we know that my known numbers are the 36.71, and the 2 is my estimate. So my error value is going to be plus or minus a 5 in that last spot. So I'm in the thousandth spot. We're always going to use 5 for the instruments that we have. We don't have the most precise instruments out there, so our error really could be half of that last one that we're making the estimate on. So we will always use a 5 in our values there. So let's take a look at the image that we drew a while back. So if I'm looking at either of these, the error is going to be the same for this graduated cylinder no matter what. Because, remember, my estimate is my last digit. So my error for this, I would write as plus or minus 0.5. I'm in the tenths spot there, so I'm in the tenths spot here. Well, that error is the same for this this value with the same graduated cylinder, plus or minus 0.5. We don't need to write milliliters again because we have it here and here. But if you wanted to, you could. If we're using a digital instrument like that digital balance, we're going to write what it says on the scale, just like we said a few slides ago. And the error then is going to be half of where that final digit is. So if I had a value of 36.71, I'm in the hundredths spot here, but my error is to the thousandths spot. So I'm one spot out further when I'm dealing with a digital instrument. Oops. Some questions that you're likely to hear on an exam deal with problems like this. So let's say we have 6 lab groups collecting data, and we have an accepted value of 10.3 grams per milliliter. So these are all densities. They're all missing their units. That's a big no-no. A typical question you might have is, looking at the data, did the group get systematic or random error, and why? So if we look at our accepted value here, 10.03, we see that all of these values are relatively close to one another and they're all above the accepted value. So we would call this systematic error. Because it's all precise and inaccurate. And another question you might see is something like, which of these data points had the highest or best precision? So which was the most precise lab group? Well, we would say B was the most precise lab group because their error is the smallest. They have the smallest error value of all the ones here. 0.01 is smaller than 0.02,